In this video, we are going to talk about the first two lessons of Unit 4 of Honors Chemistry, which is, funnily enough, called Chemistry. Different type of video. Not one I'm probably going to ever make again, but nice to try something new. So we start off with atomic structure. We need to know the history of atomic theory. So the ancient Greeks thought that matter was composed of earth, air, water, and fire. That is a little bit inaccurate. They determined that all things are made of indivisible particles. So atomos means indivisible. Now, we find out later on that these things are divisible, but not yet. The first part of this lesson that makes it important is that you have to dumb down a little bit and forget some chemistry knowledge in order to understand the history behind it, and you have to kind of dumb down in order to actually properly learn this. In 1803, John Dalton, the same John Dalton that made up the law of partial pressure, said atoms are solid, indivisible, and indestructible. All atoms of the same element are the same, and different elements contain different size atoms. There are some flaws in this logic. You have the compounds that form by joining the atoms of two or more elements in a definite whole number ratio. In a chemical reaction, atoms are not created, destroyed, or changed into other atoms. They are only rearranged. This is his model. Then we have J.J. Thomson, which we can call the chocolate chip cookie model. Pretty much his one shows some magnetic reactions on how the light will reach the anode from the cathode if there's a magnet in a way. And this is actually why magnets can destroy electronics. They can mess up and not allow the signals to reach where they need to be, which can cause the thing to just completely shut down. So that's why when your parents tell you don't put magnets by electronics, you shouldn't put magnets by electronics. Magnets can really mess up the computer software permanently. Anyone who's taking something in computer science will know more about this than what I do. And the cathode is a negative end while the anode is a positive end. So, when an electrical magnetic field is introduced, the anode does not glow. This indicates subatomic particles, and this is what proves electrons. So this is the positive charge, and then you have the electrons. The atoms have electrons that stick out like raisins, and a positively charged sterling mass containing electrons on top of the atom. This was 1903, so a century after Dalton. You have a spherical cloud of positive charge, and then the electrons. And now we have lesson 4.2 of Honors Chemistry. This one I'm going to have a little bit more time describing. This is the modern atomic theory. So, atoms are no longer thought of as solid and unchangeable, and they do contain many parts. There are similarities to Dalton's atomic theory, though. Elements are still made up of atoms, compounds are elements stored in whole number ratios, and atoms are not changed during a chemical reaction, only rearranged. There are some problems, though. Atoms have many parts of the complex structure. Atoms of the same element are not necessarily alike, and atoms of the same element can and do have different masses. And I'm just going to take attention off the slideshow for a second because I do want to expand on what this is talking about. This is talking about isotopes, and there are different isotopes. Like, for example, carbon dating uses carbon-14. If you go look up on the periodic table and look at carbon, you'll see carbon-12. Now, in units 1, 2, and 3 of chemistry, you'll just learn to always use the AMU of that. But the more complex numbers do get involved. This is beginning to become the more fun part of chemistry. If you know anything about uranium and plutonium, they're all radioactive and they decay into different isotopes, and there's just one isotope that's really bad, and this is what I have to know to make nuclear bombs. You'll also know how there's some things like carbon-14 are radioactive and other isotopes aren't, and it's not the only one. Like cesium-137 is radioactive, and I do want to look at a few others. like I think there's a hydrogen radioactive isotope. Um, yeah, hydrogen 3. Hydrogen 3 is a radioactive type of isotope. They use this to make the hydrogen bomb, which is a type of atomic bomb, and I think it's a pretty powerful type. Hydrogen 3 is rare, though, and, like, don't freak out, because unlike things like uranium or plutonium, where every isotope is radioactive, carbon-14 is used in carbon dating, but, like, hydrogen-3 can be really dangerous, but it's very rare, because hydrogen, the average AMU is 1. So you have hydrogen-2 to get to, which is rare enough as it is, and then you have to have hydrogen-3 at the other end of it. But yes, this is where the hydrogen bomb does come from. It comes from this radioactive isotope. But, I mean, even putting isotopes to the side, because, radioactivity to the side, you have different isotopes of different elements, so the AMUs aren't always accurate, and you do have to, like, actually know what you're talking about in case of these complex scenarios, but your chem teacher should give them to you, so I wouldn't worry too much about this. So then Ernest Rutherford makes this in 1909, the gold foil experiment. Most of the particles pass straight through. Some were deflected slightly, but some were deflected severely, as in more than 90 degrees. And when we zoom in on this is the ones that pass most through. These are the ones that have slight deflections. These two are the ones that go through more than 90 degrees. So they were able to pass through the empty space between gold atoms. And provided the atoms were not like the solid spheres, that Dalton and Thomson had provided. He made a model in 1910, and it changed the model of the atom. It has centrally dense, positively charged nucleus and empty space around it where the electrons were. Most of the volume is empty space, and most of the atoms control a dense, positively charged nucleus. Electrons are present surrounding the nucleus. So, and in case you're wondering about the different isotopes, because atoms are neutrally charged until you get to the ions, which have different bonds and can be used to make molecules. Like I'll actually give you an example. In order to make sodium chloride, the chlorine takes a proton from the sodium so that they both have complete shells. Sodium has 2 complete shells, chlorine has 3. So you have 18 electrons for chlorine with 17 protons. Sodium, you have 11 protons and 10 electrons. So the chlorine has a negative charge now, and the sodium has a positive charge, and then they can go together. Whereas for hydrogen and oxygen, you need to kind of bond together in order to have this. So it's a little bit different. So yeah, the protons and the electrons, they always remain constant in an atom. So in case you're wondering about different isotopes, in order to be an isotope, it has to be a change in the neutron. Okay.